Toyota's 3.4-liter twin-turbo V6 was built to be the future of their truck lineup. Instead, it's destroying engines. This short block came out of a 2023 Tundra with 38,000 miles. Two main bearing caps spun a full 180 degrees, leaving aluminum transfer streaks across the crankshaft, while the rod journals remain virtually untouched. Toyota's official explanation is machining debris in the oil passages. But if debris were circulating through the entire oiling system, why is the damage only showing up on the mains? The real cause may point to something Toyota knew about and sold anyway. The investigation begins the moment the failed engine leaves the truck. Every step is logged, every part tagged. The short block from the 2023 Tundra, with just 38,000 miles, is sealed in a tamper-evident bag. A barcode label is fixed to the block, matching the vehicle, VIN, and time-stamped at the moment of removal. Each component, main bearing caps, crankshaft, rod bearings, is cataloged with its own barcode and photographed in place before disassembly. The images capture not just the physical layout, but the exact sequence of removal, locking in the original state of the evidence. Two technicians sign off on the chain of custody form at every handoff, from the shop floor to the teardown bench, from the bench to the metallurgical lab. The logbook records the date, time, and signature for each transfer, following ASTME1 459 guidelines for physical evidence. The process is designed to prevent any question about contamination or tampering. Parts are stored in anti-static, individually labeled bags, then placed in a climate-controlled cabinet until analysis. Each bag barcode is scanned into a secure spreadsheet, linking the physical part to its photo record and custody log. The teardown itself is documented with high-resolution, time-stamped photos at every stage. When the main bearing caps are removed, the orientation and position are recorded in the log, and the exposed journals are immediately photographed to preserve the as-found condition. The crankshaft is rotated by hand, and both the main and rod journals are inspected for signs of scoring or debris. The main caps are set aside in a marked tray, with a second technician verifying the sequence and signing the inspection sheet. Even the oil pan and timing chain tensioner are bagged, labeled, and logged, ensuring that any metallic debris found later can be traced back to its source. Before any lab work begins, the entire evidence package is checked for completeness. The technician cross-references the barcodes, photo logs, and custody forms, confirming that every part from the engine is accounted for and that no step in the process has been skipped. Only then are the components released for microscopic analysis and clearance measurements. This level of documentation means that any findings, whether they point to machining debris, oil starvation, or a design flaw, are built on a foundation of traceable, uncontested evidence. The result is a forensic record that stands up to scrutiny, allowing the technical story to unfold without doubts about how the evidence was handled. Main bearing caps from the 38,000-mile V35A block come off to reveal a scene far from ordinary. Two caps are rotated more than 180 degrees from their original positions, their alignment marks now completely out of phase. This is not the slow drift of normal wear. It is the aftermath of a sudden failure. Once the oil film vanished, friction took over, letting the bearings lock to the crankshaft and shear against the block's locating tabs. The caps, meant to fit snugly in their machined seats, now sit twisted, their parting lines polished bright from movement that should never occur in a healthy engine. Beneath those spun caps, the crankshaft journals tell their own story. Instead of the expected mirror finish, the surfaces are streaked with bright silver bands, aluminum transferred from the bearing backs. These marks run lengthwise, matching the width of the main journals. The transferred metal is soft, uneven, and ridged, catching a fingernail and showing how much heat and pressure built up as the crank bore down on a dry bearing. The contrast is sharp. The main journals look gouged and patched, while the rod journals, where the connecting rods attach, remain clean, with only faint polishing and no embedded debris or scoring. This pattern is telling. If debris from machining had been circulating in the oil, every bearing fed by the same oil gallery should show damage. Yet, the destruction is focused on the mains. The rod bearings, sharing the same pressurized oil circuit, show no corresponding wear. There is no pitting, no sign of foreign particles, no scuffing, just the uniform sheen of normal operation. That difference demands explanation. Why would debris target only the main bearings, leaving the rods untouched? A closer look at the main cap saddles adds another clue. The block's bearing seats, designed for precise alignment, are scarred where the caps spun. Locating tabs are deformed, and the cap's parting surfaces are polished from movement that should never happen. In one cap, the original stamp now sits on the opposite side of the block, a clear sign of at least a half turn of movement. Measurement with a protractor confirms more than 180 degrees of rotation on both failed mains. The thrust bearing, meant to control the crankshaft's end-to-end movement, shows only partial coverage, a visible wear arc matching just half the circumference. The older 5.7-liter V8 used a full 360-degree thrust pad, but the V35A's 180-degree design leaves half the crank unsupported, concentrating stress on a narrow band. The wear pattern is unmistakable, one arc polished to a shine, the other untouched. The timing chain tensioner, coated in a fine dark gray powder, holds metallic debris that matches the aluminum transferred onto the main journals. This is not leftover machining grit. It is the byproduct of metal-to-metal contact after the oil film failed. The evidence points to a deeper mechanical failure, raising the question of what caused the oil film to collapse at the mains and why the damage stopped there. Toyota's official stance on the V35A twin-turbo V6 failures is laid out in the recall documents filed with the National Highway Traffic Safety Administration. According to Recall 24V381, the problem stems from machining debris left in the engine's oil passages during production. The recall covers 2022 to 2024 Toyota Tundra and Lexus LX models, as well as 2024 and 2025 Lexus Sequoia vehicles, totaling 127,000 units. In Toyota's words, the defect is described as a potential for catastrophic engine failure due to spun main bearing journals. Their investigation claims that residual metal particles, averaging 30 to 45 microns in size, remained in the oil passages after the final machining step. These particles, according to the report, can enter the oil pump discharge flow, block oil delivery to the main bearings, and trigger localized oil starvation. The company specifies that the debris originates from the final bore finishing operation, and that insufficient flushing allowed these particles to persist in the oil circuit. Toyota's recall bulletin states explicitly that the presence of this debris is the sole identified cause of the observed main bearing failures, and that no design-related weakness, material defect, or lubrication system flaw was found. The remedy offered is a full replacement of the powertrain assembly, including engine, transmission, and oil pump, with a new unit that has undergone updated cleaning procedures. The replacement engine will receive an upgraded main bearing cap design with 360 degrees of thrust bearing coverage, Dealers are instructed to flush the oil passages with certified solvent, replace the timing chain tensioner, and verify oil pressure sensor operation. Toyota assures owners that the repair will be performed at no charge and completed within a standard service bay visit, with no further maintenance required after the fix. This language places the blame squarely on leftover debris from manufacturing, not on a flaw in the engine's design or assembly tolerances. The company's position is clear. Machining debris is responsible, and the recall's cleaning and replacement procedures are intended to eliminate the risk of future failures. The next step is to examine whether the physical evidence from failed engines truly matches this explanation. A detailed look at the V35A's oiling circuit exposes a fundamental flaw in the debris explanation. According to Toyota's own service manual, the pressurized oil moves from the pump into a main gallery that feeds both the main bearings and the connecting rod bearings. This means that any debris left in the oil passages would travel the same path, reaching every bearing surface along the way. If metal particles were truly circulating in the oil, damage would not stop at the main journals. The rod bearings, which receive oil directly from the same drilled passages off the crank, would show similar scoring, pitting, or embedded particles. Yet, teardown after teardown reveals the opposite. The rod bearings are nearly untouched, their surfaces smooth and uniform, showing only the faint polish of regular use. The oil then continues to the camshaft bearings and timing chain tensioner, both of which are also part of the pressurized system. If debris were present in the oil, these components would not escape unscathed. Cam journals would display grooves or scoring, and the tensioner would be marked by more than just the powdery residue seen after main bearing failure. Instead, the only significant metallic debris found in the tensioner chemically matches the aluminum transferred from the failed main bearings themselves, not machining grit or foreign particles. A schematic of the V35A's lubrication system underscores the point. A single gallery distributes oil to all critical rotating parts. The selective destruction of the main bearings, while the rods and cams remain clean, contradicts the idea of a system-wide contaminant. The evidence points away from random debris and toward a local failure in oil delivery or bearing fit at the mains. The pattern of wear simply does not fit the model Toyota describes. This mismatch between theory and observation forces a closer look at the engine's design, tolerances, and oiling strategy. An engine builder stands over the stripped V35A block, calipers in hand, ready to measure what cannot be seen with the naked eye. With the crankshaft out and the main cap set aside, a thin strip of plastigauge is laid across the main journal. The cap is torqued to factory specification, then removed. The imprint stretches wider than the gauge's 0.03 of an inch mark. The reading is 0.05 of an inch. That is more than double the upper limit Toyota specifies for this engine. The builder points to the spec sheet. 1/1000th to 1.2 thousandths of an inch is the target, with anything above 1.2 thousandths of an inch considered out of bounds. Here, the gap is so wide that oil cannot maintain a stable film, especially when the engine is under load or at low RPM. This is not an isolated case. Multiple teardown reports from independent shops and from warranty returns have documented the same oversized clearances. The builder checks the alignment of the oil groove on the upper bearing shell. It is off-center by nearly 0.2 of a millimeter, enough to throttle oil flow and starve the bearing face. With a bore scope, the camera reveals the groove's edge shadowing the oil feed hole. It is a subtle misalignment, but one that matters when tolerances are this tight. Attention turns to the thrust bearing. Unlike the older 5.7L V8, which used a full 360-degree thrust pad to control crankshaft movement, the V35A relies on a 180-degree design. Only half the crank's rotation is supported against end-to-end movement. The wear arc on the thrust face is polished to a bright crescent, while the opposite side remains untouched. Under heavy acceleration, or when towing, all the force is concentrated on that narrow band. Finite element analysis from independent labs shows that stress at the unsupported arc can exceed the material's fatigue limit, especially if oil pressure drops or clearances are too loose. The engine builder inspects the timing chain tensioner next. The part is coated in a dark, powdery residue. A magnet picks up nothing. It is not steel, but aluminum, chemically matching the material transferred from the main bearings during metal-to-metal contact. The builder points out that this debris is not leftover factory grit. It is the aftermath of the bearing's own destruction, not the cause. Every measurement and observation lines up. Oversized main bearing clearances, partial thrust pad coverage, groove misalignment, and aluminum debris generated after oil film collapse. The evidence does not support a random event caused by stray particles. Instead, it paints a picture of an engine built on the edge of its tolerances, where a small deviation can start a chain reaction leading to catastrophic failure. The builder's tools and careful readings make clear that the problem is deeper than a single batch of dirty parts. The problem is built into the hardware itself. Engineers have spent months tracing the chain of failure, but one clue keeps surfacing: sudden, short-lived drops in oil pressure that line up with the moment's engines die. Digital logs from dealership OBD scanners show oil pressure plunging from normal, sometimes as high as 18 pounds per square inch, down to just 4 or 5 pounds per square inch for nearly 2 seconds during idle or after letting off the throttle. In multiple cases, the gauge even hits zero right before the engine locks up. These are not random readings. They are repeatable, and they match what independent shops see on their own test benches. A university lab ran computational fluid dynamics models using the V35A engine's actual oil pump geometry. The simulation shows that at low revolutions per minute, especially after a cold start or during city driving, the pump cannot keep up with demand. The pressure troughs predicted by the model, lasting between 0.8 and 2.3 seconds, match exactly with the field data. During these dips, the oil film separating the crankshaft from the main bearings collapses, leaving bare metal grinding against metal. The result is catastrophic. The main bearing spins, aluminum transfers to the journal, and the engine is finished. But the story does not end with oil pressure alone. Measurements on failed engines reveal main bearing clearances as wide as 0.005 inches, more than double Toyota's specified maximum of 0.0012 inches. That extra gap means the oil film is thinner and more likely to break down under stress. Add in the V35A's 180-degree thrust bearing, which only supports half the crankshaft's end-to-end movement, and you have a perfect storm. Under heavy load or towing, all the force is focused on a narrow arc, raising the risk of failure if oil pressure drops even briefly. Replacement engines issued under the recall come with a revised oil pump and a full 360-degree thrust bearing. But the fix does not address the underlying tolerance issue if the main bearing clearance is still out of spec. Owners who have already received a new engine report persistent anxiety, as some replacement units have failed again, suggesting that the core problem is not fully solved by swapping parts alone. For current owners, there are concrete steps to reduce risk: First, locate your VIN and check Toyota's official recall portal to confirm if your vehicle is covered. Next, ask your dealer or an independent shop to run a digital oil pressure test using a gauge that reads down to 0. The engine should show at least 15 pounds per square inch at 2,000 revolutions per minute and never dip below 5 pounds per square inch at idle. If your readings fall short, demand immediate inspection. After any engine replacement, insist on a Plastigauge clearance check for the mains. Results should land between 0.0010 and 0.0012 inches. Verify that the thrust bearing covers the full 360 degrees and that the oil pump part number matches the post-recall update. The mechanic's verdict is blunt: until bearing clearances are consistently within spec and oil pressure is stable across all driving conditions, these engines remain at risk. The evidence points to a design and manufacturing problem, not just leftover debris. The checklist is simple: VIN lookup, pressure test, clearance check. But the peace of mind it brings is hard to put a price on. Right now, thousands of late-model Tundras and Sequoias still rely on an engine whose failure mode remains unresolved. As Toyota's official narrative faces mounting forensic contradiction, every new mile is a test of truth versus liability. Until root causes are openly addressed and fixed, owners carry the risk and the questions every time they turn the key. What's under the hood shouldn't be a gamble. Share your experience below.